Welcome to this presentation of the paper Wideband mmWave Massive MIMO Channel Estimation and Localization with first author Weng. My name is Wymeersch and I'm a professor at Chalmers University of Technology in Gothenburg, Sweden. This paper is related to multidimensional channel parameter estimation in the context of wideband effects. This problem is of relevance to both communication and localization applications. These are two papers that tackle this problem from the localization and communication perspectives. We consider a scenario with a transmitter and a receiver. The transmitter is a base station, the receiver a user device, a UE, each equipped with an array in a multipath environment. The transmitted wideband signal goes over the air via the line-of-sight path, as well as non-line-of-sight paths via the objects. The receiver, the UE, estimates the multipath delays, angles of arrival, angles of departure. These are then used for localizing the user. Let's now look at the conventional channel model between an individual transmit and an individual receive antenna. These are indexed by M1 and M2. The channel response comprises L paths, each with a delay and a phase rotation due to the carrier frequency. The delays can also be related to the antenna indices, assuming that the reference phase is absorbed in the complex channel gain alpha. This allows us to express the channel in the frequency domain with subcarrier index k, where we see the channel gains, alpha, phase rotations due to delay of path L, phase rotations across the base station array, phase rotations across the subcarriers, and phase rotations across the user array. We can then combine all of these channel entries into a three-dimensional complex tensor H1. Suppose now that the transmitter sends a sufficient number of pilot signal so that the receiver can estimate the complex tensor. This can be done, for instance, using least squares techniques. We can then decompose the tensor in a standard form using an outer product of steering vectors in the different dimensions. Each of the steering vectors has a similar structure but different interpretation. They can refer to angles and others to delay. This kind of structure is well suited for applying three-dimensional esprit, which is a standard method that provides estimates of the different path parameters in closed form. It is important to note that these estimates are paired automatically, which means that each delay is paired with the corresponding angle of arrival and angle of departure. The attentive viewer may have noticed that we neglected one part in the channel response. In fact, the delay between the antenna elements should appear also as an actual delay, not just a phase rotation. This delay is now added in red. Often this delay in red can be ignored since the amount of the delay is negligible compared to the inverse of the bandwidth. However, when antennas are large or the bandwidth is large, this approximation without the red part is not correct. We recall that we can express the delay between the different antenna elements at the base station and user as a function of the antenna element indices. And this can then be further expressed in the equation at the bottom as a function of the carrier frequency and the antenna indices. With these new notations, we can now express the channel in the frequency domain between transmit antenna M1 and receive antenna M2, where now the red terms have been added. We see that effectively the array steering vectors have become frequency dependent, which is the wideband effect of interest. We can now collect the channel entries into a tensor, and we see that we can no longer write this tensor as the outer product of steering vectors, but there is now a new matrix or a new tensor DL, which creates a coupling between the dimensions. We can ignore this coupling, but we will see that this may lead to channel parameter estimation errors. Note that in the narrowband regime, the tensor DL just comprises all ones. Since we now have two models, one simple, the narrowband model, and one more complex, the wideband model, it is natural to ask which model can be used when. This slide aims to provide an answer to this question. The entries in DL that represent the difference between the conventional narrowband and the more complex wideband channel are shown here. In the narrowband model, again, these entries are all equal to 1. When we perform a first-order Taylor series approximation and assume that lambda over 2 spacing is applied at both arrays, we find the following condition for the narrowband channel model to hold. It basically says that the signal bandwidth normalized by the carrier frequency should be much smaller than the inverse of the sum of the elements of the 2 arrays, up to some correction terms. So, when either the bandwidth becomes large or the arrays are large, the narrowband model is incorrect. The next question is then, how do we estimate the channel parameters under the wideband model? We could of course apply 3D Esprit, but this is no longer matched to the channel model. Here we propose a new channel estimation method for the wideband channel. We first consider the channel matrix for each of the subcarriers. This is of a standard form suitable for 2-dimensional Esprit, which provide us with the angle of arrival and angle of departure, as well as the complex channel gain for that subcarrier. These estimates are provided for all of the paths. Then we can, in theory, compute the delay for all paths by combining the information across the subcarriers. However, we are not guaranteed that the paths preserve the ordering across subcarriers. This means that path 1 in subcarrier 1 may become path 5 in another subcarrier. To address this, we propose the following approach. The overall structure of our method is shown here. First, we break up the 3D tensor in 2D matrices, one per subcarrier. Then we perform 2-dimensional Esprit per subcarrier, which gives us paired angle of arrival and angle of departure, but, as we said, does not preserve the ordering of the paths. To correct the ordering, we apply k-means clustering, which is a type of unsupervised learning, which we will explain soon. Once the ordering is corrected, we can apply the method from the previous slide to compute the delay per path. Finally, once we have the paired angle of arrival, angle of departure, and delay per path, we can provide those as inputs to the localization algorithm. This figure visualizes what happens across the subcarrier when we apply 2D Esprit. This is a scenario with 3 paths. The 2 axes in the figure show the angle of arrival and angle of departure, and the different colors represent the different estimated paths across the subcarriers. We see, for instance, the following. Path 3 is provided as a second output by 2D Esprit for all of the subcarriers. These are shown in the blue triangles. This is because in the singular value decomposition inside of 2-dimensional Esprit, the third path has the largest singular value for all of the subcarriers. So for this path, there is no problem and no reordering. On the other hand, path number 1 and path number 2 become mixed in the 2D Esprit. This can be seen by the mixture of the purple and the green shapes. Again, this is because of the ordering of the singular values is not preserved across the subcarriers. The good news is that when we look at the figure, it's clear that as long as the different clusters don't overlap, we can apply k-means clustering to fix this issue and recover an ordering that is consistent across all of the subcarriers. This is what happens after we apply k-means. The paths are clustered correctly and the cluster centroids are identified, which are then the final angle of arrival and angle of departure. After angle of arrival, angle of departure, and delay estimation, the localization algorithm is called. We consider a simple method here and also work with several simplifying assumptions. For instance, that the base station and user are synchronized, and that the base station and user orientation are known. This allows us to have a closed form expression for the position based on the measurements. Here, f1 and f2 are unit vectors derived from the angles of arrival and angles of departure, and the matrices B and Y are provided in the paper. Let's now look at some results. We consider a case with 32 antennas at the base station and the user, and we will vary the bandwidth at the 28 GHz carrier frequency. Some of the other parameters are provided here as well. We will show results for channel parameter estimation, angles and delays, and then for localization. All results are provided in RMSE. The figure on the left shows the delay RMSE as a function of the bandwidth. The figure on the right shows the angle RMSE as a function of the bandwidth. In each of the figures, we have several curves. The red line is 3D esprit, which only works for small bandwidths. The green line is the proposed method without k-mean pairing, which involves a different delay estimation routine detailed in the paper. And finally, the red line is the proposed method with k-means pairing. In terms of delay estimation on the left, we see that the proposed method can significantly outperform the standard 3D esprit, especially for large bandwidths, where the wideband effect is more pronounced. The standard 3D esprit has a constant performance, since delay estimation is not affected by the wideband effect. In terms of angle estimation, the 3D esprit is severely affected by the wideband effect. The proposed method without pairing leads to poor results due to the path reordering. When we apply the k-means clustering, again, much better performance can be attained. The vertical lines in both figures represent the thresholds where we transition from the narrowband to the wideband regime. This indicates that with the proposed threshold, the wideband effect kicks in at lower bandwidth than conventionally believed. This means that the wideband effect should be more generally considered, even at moderate bandwidths. The final result is the localization RMSE, which of course combines angle and delay estimation results. Here we see that 3D esprit starts to degrade after around 15 MHz of bandwidth, while the proposed method keeps improving with more bandwidth, provided the k-means clustering is applied. With this, we come to the end of this presentation. We have shown that the wideband effect cannot be ignored for large arrays, even at moderate bandwidths. To accommodate this effect, we proposed a new method that combines a lower dimensional esprit with k-means clustering. Thank you for watching.